Let us look at the work of Hilbert in the Second International Congress of Mathematics in Paris in 1900. Hilbert presented his now famous at least 23 questions, which were open at the time. Some of these have been since solved, but one in particular still remains to this day of interest to this class. We're interested in the following question posed by Hilbert: to develop a mathematically, that is, the limiting processes which lead from the atomistic view or the molecular view of fluid and physics to the laws of motion of continua. We'll shortly present some progress that is made recently on this particular question since then in the last 125 some years. There's a particular answer to this question that contains an explanation to the appearance of irreversibility when going from one description to the other. Remember, just the billiard ball problem or hard sphere problem is not reversible, while the Boltzmann equations or the Navier-Stokes equations in particular are not. In the particular large limit, individual trajectories are typically irrelevant, and our goal is to describe an average or statistical behavior to have practical calculations. This average is over the particles or moleculars, which becomes indistinguishable because there's just so many. We have only a vague knowledge of the particular state of the system in initial time. We can't measure it, and even estimates mathematically are not really well defined to what reality is. And we're going to average over the particular initial conditions even. You might be familiar with this in computational fluid dynamics. At the initial time, we'll start with a particular distribution. We'll call that f sub n sup 0 at Zn. And the probability that f is at some t of this particular distribution times 0 is referred to the n-particle distribution function. We'll assume that this assumes that for all permutations, a sigma from 1 to n, that is f of n, obeys 191. Here, z sub sigma n is x sigma, v sigma, etc. of all the particular states, positions, and velocities. Since Fn is invariant of a particle system, the Louisville equation relative to the particle system can be defined in 192, which has its usual form for all permutations n. In a particular domain D, with particular boundary conditions for the distributions going in and out of a fluid parcel, that is part of the boundary D, such that the boundary is very, very small. There holds some distribution showing that the flow in and out of the domain will be equal, as in 194. The velocities will be related. A particular direct approach from the microscopic to macroscopic scales can be established now, and we'll be able to derive the fluid mechanics equations from particle systems, and trying to start with the following empirical distributions in space and time. One for density for all n, velocity for all n, and all energy for all n. And you can see we've just summed the densities, velocities, and energies over the domain. We'll try and use the laws of large numbers or statistics to derive principles to obtain their limiting behavior as n goes to infinity. Starting from the Boltzmann equation, it's easily possible to derive a formal or number of fluid mechanics equations, as we previously showed in the last lecture of this video series. The method goes back to those pioneered by Hilbert, Chapman, and Inskog, and it will look basically for the asymptotic expansions in the terms. If we expand the solution of f to b under the particular form of 196 of the sum of alpha to the negative n f of n, distribution. Remember, z is a function of x and v, and plug in the expansions into b, we'll be able to identify powers of alpha, giving rise to the Euler equations, as well as the viscous and compressible Navier-Stokes equations. Truncated asymptotic expansions, through these, it could be possible to do a more rigorous justification of derivation of the compressible Euler equations in a system similar to the Navier-Stokes equations. More recently, Bardos, Gulsey, and Livermore showed a program or research program for deriving weak solutions of the Navier-Stokes equations from the de Perron-Lyon solutions of the Boltzmann equations. The fundamental idea behind this concept and program is that there should be a proof which will only require estimates coming from physics, dependent on mass, energy, and entropy. The difficulty of the approach will lie in the poor understanding of renormalization solutions. Gauss and Saint-Raymond achieved this in the limit of least diffusive systems.